Welcome back to the Deep Dive, where we unearth the foundational concepts that power our digital world. Today, we're tackling something so fundamental, it happens every single time you interact with your computer, often without you even realizing it.
Hmm.
Think about your everyday experience. You're probably juggling multiple tabs in your browser, maybe streaming some music, you've got a document open, perhaps running a quick script in the background.
Yeah, the usual chaos.
Exactly. How does your single computer, with its finite resources, manage to keep all these diverse tasks humming along, creating this incredible illusion that everything's happening simultaneously?
It's easy to take for granted, isn't it? But it's a masterclass in clever engineering.
It truly is.
This seamless multitasking, this feeling of, almost limitless computing power. It's all thanks to the unsung heroes of computing.
And those are
Today, we're taking a deep dive into the very core units of work within any operating system, processes and threads. These aren't just abstract ideas, they're the literal heartbeat of your computing experience. The invisible architects orchestrating everything from a simple click to complex data analysis.
And that core understanding is precisely why our mission for you, our curious learner, is to equip you with the rock-solid grasp of these concepts.
Right.
By the end of this deep dive, you should be able to explain what processes and threads are, how they collaborate, communicate, and crucially, how operating systems manage them, all with, hopefully, ease and confidence.
Making it less mysterious.
Exactly. This deep dive is designed to transform any confusion into clarity, setting you up perfectly for your upcoming class on operating systems.
And to achieve that, we've pulled together some excellent sources. We'll be drawing heavily from a leading textbook on operating system concepts, which gives us a really comprehensive overview of the theory.
Okay, the theoretical foundation.
But theory only goes so far, right? So to truly see these ideas in action, we'll also be peeking into the design of a teaching operating system called Pintos.
Ah, Pintos. I've heard of that. It gives us a practical, behind-the-curtain look.
Exactly. How these fundamental concepts are actually implemented, down at the kernel level. It's one thing to read about it, it's another to witness how it's built, and importantly, why certain choices were made.
Okay, sounds like a great plan. Let's unpack this and start with what I think of as the foundational building block, the process.
Good starting point.
When we talk about running a program, many of us might just picture a block of code executing. But that's not quite right, is it? There's a crucial distinction we need to make right from the start.
Absolutely. It's a fundamental distinction. The core concept here is that a program is, well, it's passive. It's an inert entity.
Passive, like
Yeah.
just sitting there.
Yeah, think of it like a beautifully written recipe book sitting on your kitchen shelf. It's a static set of instructions full of potential, maybe a file stored on your disk, but it's not actually doing anything. It's inert.
Right, it just is. Static, dormant.
Mm-hmm.
But then you click an icon or type a command, and suddenly it springs to life. So a process, that's the active thing.
Exactly. The process is the active entity. Following our analogy, the process is the chef in the kitchen, actively taking that recipe, gathering ingredients, following the steps, and actually cooking the meal.
Ah, I like that. The chef doing the work.
So when you launch an application, say your favorite web browser, you're not just looking at the program file anymore. You've initiated a dynamic executing process. You've brought that static recipe to life.
Okay, so what makes it active? What components does this chef have?
Well, it's much more than just the code itself. Every process has its own program counter.
Who does?
Like the chef's current instruction pointing to the next instruction to be executed, it guides its flow through the program.
Got it. The step it's currently on.
Right. It also has its own set of associated resources. Dedicated memory regions,
Whoa.
any open files it's using like your browser's cache or history file, and maybe even I/O devices it's interacting with like your keyboard or network card.
And when we talk about its memory, we're talking about several distinct regions, right? It's not just one big blob, but a carefully organized workspace.
That's a great way to put it, a very organized workspace. There's the text section, which is where the executable code, the recipe steps resides. Then the data section for global variables, the ingredients that are always on the counter, let's say.
Okay. Text is code, data is globals. What else?
You've got the heap. This is dynamically allocated memory that typically grows upward in the address space. It's used for things you create during runtime. Think of it as extra workspace you might need unexpectedly, maybe to prepare a complex garnish.
Dynamic memory.
Yeah.
And the stack.
And finally, the stack, which usually grows downward. It's used for function calls, local variables, return addresses, like the individual prep stations for each step of the recipe. Each of these regions is critical for the process to function dynamically.
Text, data, heap, stack. Got it.
That's a great breakdown of the process's internal world. These distinct components give the process its dynamic nature and its ability to act as an independent unit of work.
So when you click that web browser icon, the OS does a lot of setup. Loads the code, sets up these memory regions, points the program counter to the start.
And voila, you have an executing process ready to go.
Yeah.
It's a testament to the OS's role as a sophisticated resource manager.
Now, once a process is born, it doesn't just stay in one state until it dies, right? It goes on quite a journey through various states.
That's right. It's not static.
What kind of journey does it embark on once it's created? How do those different stages influence what the OS needs to do?
That's a crucial question, because these states aren't just labels. They're how the OS manages everything. It's the conductor score, allowing it to juggle hundreds of applications.
Okay, so what are the states?
A process starts in the new state when it's initially being created. From there, it usually moves to ready.
Ready means?
It's loaded into main memory and is basically waiting its turn for the CPU. It's ready to run, just needs the processor.
Okay.
Then when the CPU scheduler picks it, it transitions to the running state. This is where its instructions are actually being executed. The chef is actively cooking now.
New, ready, running. Makes sense. And what about when our web browser process needs something from the outside world? Like if it needs to fetch data from a server or load a file from disk, it can't just keep the CPU to itself while it waits, can it?
Exactly. That's a perfect example of when it enters a waiting state. If a process needs to perform an I/O operation, reading from disk, waiting for network data, maybe waiting for user input, or even waiting for a child process to finish it, gives up the CPU. Because waiting for I/O is slow. Letting it hold the CPU would be incredibly wasteful. So the OS puts it in the waiting state and assigns the CPU to another process that's in the ready state.
Efficient. So it waits, gets its data, then what?
Once that I/O operation completes, or the event it was waiting for occurs, it transitions back to the ready state, waiting for its turn on the CPU again.
Back in line for the CPU?
Yep. And finally, when it finishes its execution or is explicitly shut down, it moves to the terminated state. Its resources can then be cleaned up by the OS.
New, ready, running, waiting, terminated. That's the life cycle.
That's the basic life cycle, yes.
So these states are the very mechanism by which the operating system manages resources so efficiently. It creates that seamless illusion of multitasking.
Precisely.
The OS isn't actually running everything simultaneously on a single core. It's rapidly switching between processes that are in the ready state, giving each a little slice of CPU time, like a world-class juggler keeping all the balls in the air.
Exactly. Think about how your phone manages apps. When you switch between them, the OS is constantly managing these process states, moving applications in and out of the running state. Some apps might be waiting for network data, others ready to resume computation.
And our source mentioned Google Chrome using a multi-process model.
Yeah, that's a great practical example. Chrome often runs each tab, and sometimes even extensions or plugins within a tab, as its own separate process.
Why would they do that? Seems like it might use more resources.
It might, but the big advantage is robustness and isolation. If one tab crashes because of some faulty JavaScript or a buggy plugin,
It doesn't bring down the entire browser.
exactly, or worse, your entire system. The misbehaving process is contained. It's an ingenious design decision, trading some resource overhead for significantly enhanced stability and security. One process can't easily mess with another's memory.
That makes a lot of sense, especially for something as complex as a modern browser. Okay, so we know what a process is and its life cycle. How do they actually come into existence, especially in a system like UNIX? There's a classic dance of system calls, right?
Ah, yes, the famous UNIX fork and exec dance. It's a very elegant pattern.
A sort of two-step. First, create a copy, then transform it. This pattern feels foundational to the UNIX philosophy.
You've hit on a UNIX superpower there. The fork, system call, creates a new process known as the child process.
And this child is?
It's a near duplicate of the calling process, the parent. It inherits a copy of the parent's memory space, its program counter, pointing to the instruction right after the fork, and copies of its open file descriptors at that specific moment.
Oh, it's like cloning the parent.
Essentially, yes, you go to clone, but it has its own unique process ID, PID.
Yeah.
So after fork, you have two processes, parent and child, running the same code from the point fork, returns. They can check the return value of fork to know whether they or the parent or the child.
So, after fork, you have two almost identical processes running the same code. But often the child isn't meant to just be another copy of the parent, is it? it usually needs to do something different.
Correct. Very often, the first thing the child process does after the fork call returns is to call one of the exec family of system calls.
And exec does the transformation.
Exactly. The exec system call replaces the child's entire current memory space, its code, data, heap, and stack segments, with a new program loaded from disk. So the child process effectively becomes a new, entirely different program.
Ah, okay, so fork creates a clone, and exec overlays that clone with a new identity.
Precisely. Our textbook source has a great example in Figure 3.9. It shows a C program where a parent process calls fork. The child process then checks its PID and calls exit builds else enroll L.
So the child becomes the else command.
Yes, it loads and runs the else program, listing directory contents while the parent might continue doing something else. This demonstrates how a process can launch a completely new, unrelated task.
That's a fantastic example. The parent creates a clone, and the clone then decides to go off and become something entirely different, like a superhero creating a sidekick who then embarks on their own mission.
That's a fun way to think about it.
And the parent often needs to keep track of its children, maybe wait for their mission to complete. That's where wait comes in, right?
Yes, exactly. The wait system call, or related calls like wait PID, allows the parent process to pause its own execution. It essentially puts itself into a waiting state.
Ah, back to the states.
Yep, back to the waiting state. Specifically, waiting until one of its child processes terminates. This does two key things. It lets the parent retrieve the child's exit status. Did it succeed? Did it fail? And it allows the operating system to fully clean up the terminated child process's resources. It's crucial for coordination and keeping the system tidy.
So this fork exec wait pattern is really fundamental in UNIX-like systems.
Absolutely. It enables an elegant system design where any program can effortlessly launch and control entirely new, independent tasks. It's the backbone of everything from your command line shell interpreting commands to complex server processes managing worker tasks, all built on this fundamental cloning and transformation dance.
Okay, so we've established processes as these robust, isolated actors. Now, a critical question. How does the operating system, which hosts all these potentially unruly actors, protect itself and protect other processes from interference? This gets us to process isolation, doesn't it?
You've hit on a cornerstone of system stability and security. The OS, the Grand Manager, must ensure that a user program can't accidentally, or worse, maliciously corrupt the kernel's own data structures or fiddle with the memory of another user's program.
That seems essential. How is it enforced?
The primary mechanism is hardware-based, using something called the mode bit.
The mode bit. Sounds simple, yet powerful.
It truly is. The mode bit typically has two states, 0 for kernel mode, also called supervisor mode, privilege mode, and 1 for user mode.
So when I'm running my browser or word processor, it's in user mode.
Generally, yes. When the computer is executing code on behalf of an application you launched, it's in user mode. This is restricted environment. Certain instructions that could directly harm the system, like manipulating hardware directly, changing memory mappings, or disabling interrupts, are simply disallowed by the hardware when in user mode.
Okay, but what if my word processor needs to save a file? That involves talking to the disk hardware, which sounds privileged. It can't do that directly from user mode, right?
Precisely. It has to ask the operating system for help. That's where system calls come in.
Ah, the bridge between user and kernel.
Exactly. When a user application needs a service from the OS that requires privileged access, like file I/O, network access, process creation, memory allocation, it invokes a system call. This is usually done via a special trap instruction.
A trap, like a deliberate interrupt.
You got it. It's essentially a software-generated interrupt. This trap instruction causes the CPU to switch from user mode to kernel mode. The mode bit flips to 0 and transfers control to a specific predetermined entry point within the operating system's kernel code.
I recall reading something about in Alta by $30 being used for system calls in the Pintos OS on the 80 by 86 architecture. How does that work at a low level?
That's a great specific example.
Yeah.
N530 is the software interrupt instruction used by Pintos and older Linux versions on x86. When this instruction executes in user mode, the CPU immediately 1. Pushes some state, like the current flags, code segment, and instruction pointer, onto the kernel stack. 2. Looks at the address of the interrupt handler for interrupt number 0 by 3048 decimal in a special table called the interrupt descriptor table, IDT. 3. Sets the mode bit to kernel mode, 0. 4. Jumps to that handler address in the kernel.
Wow, okay, so it's a very controlled handover.
Extremely controlled. The kernel handler then figures out which specific system call the user program requested, usually based on a value in a register, like EAX, validates the arguments passed by the user program, a crucial security step, performs the requested operation with full kernel privileges, places the result back in a register, and then executes a special return from interrupt instruction, like IRET, to switch back to user mode and resume the user program right after the int $30 call.
That's intricate but makes sense for security. What happens if a user program tries to be naughty or just buggy, like it tries to execute a privileged instruction directly or access memory it doesn't own?
The hardware catches it. That's another critical role of hardware protection working with the OS. If a user program attempts an illegal operation, invalid instruction, invalid memory access, division by zero, the hardware itself detects the error and generates another kind of trap, often called an exception or a fault.
So another automatic transfer to the kernel.
Yes. Control transfers back to the operating system, again in kernel mode. The OS then looks at the cause of the trap. If it's a recoverable error, like a page fault, which we'll discuss later, it might fix it.
Yeah.
But if it's a fatal error, like accessing forbidden memory,
The OS terminates the process.
usually, yes, it terminates the offending program abnormally, often logging an error, maybe generating a core dump for debugging, and cleans up its resources. This prevents a single faulty application from bringing down the entire system or corrupting other processes. It's essential protection.
Speaking of terminating processes, the source also mentioned zombie and orphan processes in UNAX. Those sound a bit spooky. What are they?
They do sound a bit macabre, but they're important concepts related to process termination in UNIX-like systems. A zombie process isn't actually running, it's already terminated.
Dead.
Technically, yes. But its entry still exists in the kernel's process table. This happens when a child process terminates. But its parent process hasn't yet called wait, or wait-tipped, to retrieve the child's exit status.
So it's dead but not yet reaped by the parent.
Exactly. The process itself is gone, using almost no resources except that small process table entry containing its exit status. It's waiting for the parent to acknowledge its demise. Usually this is temporary, but if the parent is buggy and never calls wait, zombies can accumulate, though they're generally harmless unless you run out of process table slots.
Okay. Dead but waiting for acknowledgement. What about an orphan process?
An orphan process is the opposite situation in terms of parentage. It's a process whose parent has terminated before the child has finished executing.
So it's left without a parent who looks after it.
The system doesn't just leave it running wild. In UNIX systems, orphan processes are typically adopted by a special system process, usually the init process, which has PID1.
The ancestor of all processes?
That's the one. Init becomes the new parent and will eventually call wait for the orphan when it terminates, ensuring it gets cleaned up properly. It's the OS's way of providing foster care for processes whose parents disappear.
Zombies and orphans. Interesting edge cases in process management. Okay, so we've built these incredibly robust, isolated fortresses for each process using hardware modes and system calls. That's fantastic for security and stability, but what happens when these fortresses need to talk to each other? They need to exchange blueprints, send supplies, coordinate actions. How do they bridge that chasm of isolation?
You've hit on the next fundamental challenge. Once you have strong isolation, you need controlled ways to allow interaction. That's precisely why we have interprocess communication, or IPC.
The diplomatic channels and trade routes.
Exactly. The OS provides these mechanisms, allowing isolated processes to interact and cooperate without compromising their individual integrity or the system's stability. Without IPC, processes would be completely siloed, unable to work together on complex tasks like, say, a web server passing a request to a database process.
Okay, so they need to interact. What are some of the main ways they can do that? What's the most direct approach?
One of the fastest ways for processes on the same machine to communicate is through shared memory.
Shared memory. Sounds simple enough.
The concept is straightforward. The operating system helps set up a specific region of physical memory that is then mapped into the virtual address space of multiple processes.
So multiple processes can see and access the exact same chunk of RAM.
Correct. Once this shared region is set up, processes can read from and write to it directly, just like accessing their own private memory. There's very little OS intervention needed for the actual data transfer once the setup is done.
That sounds incredibly fast. No system calls needed to pass data back and forth, right? The data is just there.
Blazing fast, comparatively.
And this feels like a big but. That speed must come with a significant cost or danger, doesn't it? if everyone can write to the same place.
It absolutely does. That's the critical trade-off. The inherent problems with shared memory are primarily protection and, crucially, synchronization.
Synchronization, meaning making sure they don't write at the same time and corrupt the data.
Exactly. Because multiple processes can simultaneously try to modify data in that shared region. You can easily run into race conditions, inconsistent reads, and outright data corruption if you don't carefully coordinate their access. The OS basically says, here's your shared whiteboard, but figuring out who gets to write when and making sure it doesn't become gibberish, that's your problem now, programmer.
So, high performance, but high responsibility for the developer to implement locking or other synchronization mechanisms, which we'll probably get to later.
Precisely. It's a powerful tool, but it demands rigorous discipline.
How does a programmer actually set this up? Our sources mention the PO6 API.
Yeah, the PO6 standard provides system calls for this. A process typically first creates or opens a named shared memory object using shmopen. Then it uses fruncate to set the size of the shared object. Finally, it maps this object into its own address space using map, the memory mapping call.
Okay.
The C code example in figure 3.14 in the textbook shows these steps, illustrating the setup required to get that shared space ready before any actual communication happens. Other processes can then open the same named object and map it into their own space.
Okay, so shared memory is fast, but requires careful manual synchronization. What if you need a more controlled, structured way for processes to interact? Maybe one where the OS helps a bit more with the coordination.
That's where message passing comes into its own. It offers a different model.
How does it work?
Instead of directly sharing memory, processes communicate by explicitly sending and receiving messages. Think of it like sending letters or packages between processes.
Okay, more like mail than a shared whiteboard.
Exactly. This is typically done using two fundamental, often atomic primitives provided by the OS send to transmit a message and receive to accept one. The OS kernel acts as the intermediary, handling the transfer of the message from the sender space to the receiver space.
Does that add overhead compared to shared memory?
Yes, definitely. Copying the message data between the kernel and user spaces takes time. However, the big advantage is that it often simplifies the programmer's synchronization burden, as the send and receive operations themselves can provide some level of coordination.
How do processes know who to send messages to or receive from?
There are different addressing schemes. In direct communication, both the sender and receiver explicitly name each other, like send, process P message, sends to P, and receive, process Q message, waits specifically for a message from Q.
Okay, direct point to point.
Right. There's also indirect communication where messages are sent to and received from mailboxes or ports. Processes communicate by sharing a common mailbox. This decouples the sender and receiver more. And sometimes you see asymmetric direct communication where only the sender names the recipient and the receiver just accepts a message from anyone.
And how do these messages actually get buffered? Like, does the sender have to wait for the receiver to be ready? Is there a post office holding the mail?
Essentially, yes. There's usually a temporary queue managed by the OS. How that queue is managed defines the buffering capacity, which affects the synchronization behavior.
Okay, what are the options?
You have three main possibilities. 0 capacity. The queue has length 0. The sender must block, wait, until the recipient calls receive. This forces tight synchronization, often called a rendezvous.
Sender waits for the receiver. Got it.
Then there's bounded capacity. The queue has a finite, fixed size, say n messages. A sender blocks if the queue is full. A receiver blocks if the queue is empty. This allows for some decoupling, but still provides flow control.
Okay, like a standard mailbox that can get full?
And finally, unbounded capacity. The queue theoretically has infinite length. The sender never blocks, as it can always add the message to the queue. The receiver might still block if the queue is empty. This offers maximum decoupling, but can potentially lead to memory exhaustion if the producer runs far ahead of the consumer.
0, bounded, unbounded capacity. Different trade-offs in synchronization and buffering. The textbook illustrates this with the classic producer-consumer problem, right?
Yes, figure 3.15 and figure 3.16 show a neat example. A producer process generates items and uses send to put them into a shared buffer, managed via message passing, and a consumer process uses receive to get items from the buffer. The message passing primitives handle the coordination, ensuring the producer waits if the buffer is full and the consumer waits if it's empty, without them needing direct access to the buffer's internal structure or complex locks.
It's a foundational pattern for understanding how message passing helps processes cooperate safely.
Exactly. It elegantly solves coordination problems. Now, these mechanisms, shared memory and message passing, are typically for processes on the same machine. But the world of IPC extends much further across networks.
And that brings us to things like sockets, right? I hear about those constantly with web stuff, networking.
Precisely. Sockets are the fundamental abstraction for network communication. Think of a socket as an endpoint for communication. A pair of processes communicating over a network, like your web browser and a web server, will each use a socket.
What identifies a socket?
It's identified by the combination of an IP address, which machine, and a port number, which application or service on that machine. For instance, your browser creates a socket with its IP and a temporary port and connects to the web server's socket, which is listing on its IP address, and the well-known port 80 for HTTP traffic.
Ah, okay. IP address plus port number equals a unique endpoint. And this forms the basis of the client-server model.
Absolutely. A server process typically creates a socket, binds it to a specific port, like 80 for web servers, 21 for FTP servers, and then listens for incoming connection requests from clients. A client process creates a socket and connects to the server's IP address and port. Once the connection is established, they can send and receive data through their respective sockets.
What's truly fascinating here is how sockets extend the concept of IPC beyond a single machine.
Right. It enables processes to communicate across local networks, or even the entire internet. It's really the backbone of almost all network communication we use daily.
So sockets are for sending streams of data between machines. What about when you want something that feels more like making a function call, but on a remote machine, without getting bogged down in socket details and data formatting?
That's the perfect use case for remote procedure calls, or RPCs.
Making remote look local.
Exactly. The core idea is to abstract away the complexities of network communication. An RPC allows a client process to invoke a procedure or function on a remote server host as if it were just a normal, local procedure call in its own code. It aims to make distributed programming conceptually simpler for the developer.
That sounds magical. How does it hide all the network stuff? There must be some behind-the-scenes plumbing.
There definitely is. It relies heavily on components called stubs. Think of them as local proxies or stand-ins for the remote function. On the client side, when the client calls the remote function, it's actually calling a local client-side stub. This stub takes the parameters you provided, packages them up into a standardized network-friendly format, a process called marshalling or serialization.
Packaging the arguments for travel.
Right. It then handles sending this marshaled message across the network, often using sockets underneath, to the server. On the server side, a server-side stub receives the message, unpacks the parameters, unmarshalling them back into their original format, and then makes the actual local call to the real procedure on the server.
And if the procedure returns a value,
The process happens in reverse. The server-side stub marshals the returned value, sends it back, and the client-side stub unmarshals it and returns it to the original caller. The stubs effectively hide all the network communication and data conversion logic.
it's clever. But I've heard one tricky aspect of RPCs is ensuring reliability. Something about exactly once versus at most once execution. What's that about?
That's a significant challenge inherent in distributed systems, unlike local calls. Networks are unreliable. Messages can be lost, duplicated, delayed, or the server might crash after performing the operation but before sending the reply.
So the client might not know if the call happened. Or worse, it might happen multiple times if the client retries.
Precisely. And at most once, semantic is the easiest to guarantee. The remote procedure will be executed either once or not at all. If the client doesn't get a reply within a timeout, it assumes failure, even if it actually succeeded. Achieving exactly once semantics is much harder. It requires more complex protocols, perhaps involving unique transaction IDs or timestamps, to detect and filter out duplicate requests caused by retries, ensuring the operation truly happens exactly one time despite network issues.
Okay, so RPCs provide a nice abstraction, but come with their own set of distributed systems challenges. Now, for simpler communication, offered between related processes like a parent and child within a Unix system, we have pipes, right? They feel like a very classic fundamental Unix tool.
Yes. Ordinary pipes in UNICEX are a very common and straightforward IPC mechanism, particularly useful for connecting the standard output of one process to the standard input of another.
Like in the shell, using the symbol.
Exactly. That symbol typically creates an ordinary pipe. Under the hood, they're treated by the OS as a special type of file, but they exist only in memory and have a limited buffer size. They're accessed via the standard read and write system calls, just like files.
And they usually connect a parent and its child.
That's the most common use case. A parent process creates a pipe, which gives it two file descriptors, one for reading and one for writing. When the parent then forks a child, the child inherits copies of these file descriptors. The parent can then close the end it doesn't need, for example, the read end, and the child closes the end it doesn't need, example, the write end, establishing a unidirectional communication channel between them.
Very neat. Data flows in one direction through the pipe.
Correct. Our source material mentions a programming project example, file copy, exercise 3.27, which uses ordinary pipes. In this exercise, one process, say the parent, reads a file and writes its contents to the pipe, while the child process reads from the pipe and writes the data to a destination file. It's a practical demonstration of how pipes enable simple, stream-based communication between related processes, showcasing that UNIX elegance.
Okay, fantastic. So we've covered processes, these big, isolated actors, and the various ways they can communicate. But as hardware evolved, especially with multi-core CPUs becoming standard, system designers realized that just having a few heavyweight processes wasn't always the most efficient way to leverage all that computing power, particularly within a single application.
This is precisely where threads enter the picture, often called lightweight processes.
Lightweight how?
Well, with the massive shift towards multi-core CPUs, there's immense pressure to actually use those cores effectively. A traditional process typically had only a single thread of execution. To get parallelism, you'd need multiple processes. But creating processes, as we saw, involves significant overhead copying memory space. Setting up resources, plus the IPC mechanisms we discussed, can be complex or have overhead.
So threads were invented as a way to get concurrency within a single process with less overhead.
Exactly. Think back to our kitchen analogy. If a process is the entire cooking station with all its equipment and shared ingredients,
A thread is like a single chef working at that station.
perfect analogy. You can have multiple chefs, threads, working simultaneously at the same station, process. They all share the main equipment and ingredients. The process is code, data, heat memory, and the files.
But each chef is doing their own specific task.
Right. Each thread maintains its own independent execution context. It has its own program counter, tracking which instruction it's executing, its own set of registers, its immediate working values, and its own stack for its local variables and function call history.
So they share the big stuff, memory, files, which makes creating them cheap, but they have their own small, private workspace, stack, registers, PC, which lets them run independently.
You've nailed it. This sharing makes threads much lighter, faster to create, faster to switch between. A thread context switch is generally cheaper than a full process context switch because you're not duplicating all those shared resources.
And this allows for powerful parallelism within a single application.
Precisely. It makes applications more responsive or able to complete tasks faster.
Oh.
Think about a word processor. One thread could be handling your typing input, another could be doing spell checking in the background, and a third could be auto-saving your document, all seemingly happening at once because they're running as separate threads within the same word processor process, operating on the same document data.
That makes sense. Different parts of the same job happening concurrently. Now, how are threads actually implemented? You mentioned user level versus kernel level earlier.
Yes, that's a fundamental distinction in how threads are managed. It's about who knows about them and schedules them.
Okay, so user level threads.
User-level threads are managed entirely by a thread library running in user space. The operating system kernel has no idea they exist. As far as the kernel is concerned, it just sees the single process that contains all these user threads.
Advantages.
Speed. Creating, switching between, and destroying user threads is incredibly fast because it involves only library calls within the user process. No expensive system calls or mode switches to the kernel are needed.
Disadvantages. Sounds like there must be one.
A big one. If any one of the user threads within a process makes a blocking system call, like waiting for disk I/O.
The whole process blocks, including all the other user threads.
Exactly. Because the kernel only sees the one process, it blocks the whole thing. This completely negates the benefit of concurrency. If one thread is waiting for that slow I/O delivery, everyone else at the station stops working. Not good.
Okay, so that's a major limitation. Kernel-level threads must be the solution.
Yes, kernel-level threads solve that core problem. Kernel-level threads are managed directly by the operating system kernel. The kernel is aware of each individual thread.
So the kernel schedules them independently.
Precisely. The kernel can schedule threads from the same process onto different CPU cores to run in parallel. And crucially, if one kernel thread blocks on a system call, the kernel can simply schedule another ready thread, maybe from the same process, maybe from a different one, to run on that core, True concurrency is maintained.
That's a downside. More overhead.
Yep. Creating, managing, and context switching kernel threads involves system calls and mode switches, so it's inherently slower and consumes more kernel resources than managing user threads purely in user space.
So it's a trade-off between user-level speed efficiency and kernel-level true concurrency blocking resilience. How do these map in real systems? Do you map many user threads to one kernel thread or one-to-one?
That brings us to the threading models, which describe how user-level threads relate to kernel-level threads.
Okay.
The simplest is the many-to-one model. Here, you map multiple user-level threads onto a single kernel thread. It's efficient for thread management, like user-level threads, but suffers from that blocking problem we discussed. If one user thread blocks, the single kernel thread blocks, and thus all user threads block. You also don't get true parallelism on multi-core systems.
So less common now.
Generally, yes, for general-purpose OSAs. More common is the one-to-one model. Here, each user-level thread maps directly to a dedicated kernel-level thread.
One user thread, one kernel thread.
Right. This provides excellent concurrency, solves the blocking problem if one thread blocks, others can run, and allows true parallel execution on multiprocessors.
But the downside is the overhead. Creating a user thread means creating a potentially heavier kernel thread too.
Exactly. It can limit the total number of threads an application can create due to kernel resource consumption. However, this is the model predominantly used by modern operating systems like Windows and Linux. They prioritize robust concurrency and parallelism.
Okay, one-to-one is dominant. Is there anything else?
There's also the many-to-many model. This tries to get the best of both worlds by multiplexing a potentially large number of user-level threads onto a smaller or equal number of kernel-level threads, sometimes via an intermediate layer called lightweight processes, or LWPs. This offers flexibility. You can create many cheap user threads while still allowing parallelism and avoiding the blocking issue of many-to-one, as long as you have enough kernel threads available. It's more complex to implement, though.
Many-to-one, one-to-one, many-to-many. Different ways to connect the user view to the kernel reality. Now, how do programmers actually use threads? Making them accessible seems key.
Absolutely. Developers typically interact with threads via thread libraries, which provide an application programming interface, API, for creating and managing them. There are several standards and implementations. Threads, PO6 Threads, is the standard API for Unix-like systems, Linux, Mac OS, etc. It provides functions like thread create to make a new thread, thread join for one thread to wait for another to finish, thread mutex lock for locking, which we'll get to, and so on.
Okay, threads for UNIX.
Windows has its own native Win32, Win64 thread API, using functions like create thread to start a thread and wait for their single object for synchronization, like waiting for a thread to complete.
And Java.
Java has built-in thread support as part of the language in its standard library. You typically implement the runnable interface or extend the thread class, and then call the start method to create and begin execution of the new thread. The Java virtual machine, JVM, then maps these Java threads onto the underlying OS's kernel threads, usually one-to-one.
So these libraries provide explicit threading control. The programmer manually creates, joins, synchronizes threads.
Correct. You, the developer, are explicitly managing the concurrency.
That sounds like it could get pretty complicated and error-prone, especially for complex parallel tasks, keeping track of all those threads and locks.
It absolutely can be. Managing explicit threads correctly is notoriously difficult. That's why there's a significant trend now towards implicit threading.
Implicit threading. Letting someone else handle the details.
Pretty much. The idea is to shift the responsibility for creating and managing threads away from the application developer and onto compilers and runtime libraries. The goal is to make parallel programming easier and less error-prone by abstracting away the low-level threading details.
That sounds like a very welcome development. How does that work in practice?
One very common and effective technique is using thread pools.
Thread pools?
Instead of creating a brand new thread every time you need one, for example, for every incoming web request in a server, you create a pool of worker threads up front. When a task arrives, it's handed off to an idle thread from the pool. Once the task is done, the thread goes back into the pool, ready for the next task.
Ah, so you reuse threads instead of constantly creating and destroying them.
Exactly. This avoids the overhead of thread creation destruction and also limits the total number of active threads, preventing resource exhaustion. It's a hugely efficient pattern, especially for applications handling many short-lived tasks.
Makes perfect sense. What other implicit approaches exist?
Another popular one is OpenMP. It's a set of compiler directives and library routines, mainly for C, C++Mic, and Fortran. Developers add special comments or pragmas like #pragma_omp_parallel4 to their code to indicate loops or sections that can be parallelized. The compiler then automatically generates the necessary threading code to execute those sections in parallel, often using a thread pool behind the scenes.
So the programmer just hints at parallelism,
Yeah.
and the compiler does the heavy lifting.
Nice. It simplifies things considerably for certain kinds of parallelism. Our sources also mention Apple's Grand Central Dispatch, GCD, as another important technology for implicit threading on macOS and iOS. GCD manages queues of tasks, blocks of code, and efficiently schedules them onto an underlying thread pool managed by the system, adapting to the current system load. Developers just define tasks and dispatch them to appropriate queues.
So thread pools, OpenMP, GCD, always to get parallelism without manually juggling threads. That seems like the future.
It's definitely a major direction, especially as making effective use of many core processors becomes ever more critical.
How do Linux and Windows actually implement their mostly one-to-one threads at a deeper internal level?
Linux has a rather interesting perspective. It doesn't strictly distinguish between processes and threads internally in the way some other OSs do. Instead, it uses the more general term task to refer to any flow of control.
Task, okay.
The key system call is clone. It's like fork, but it allows the caller to specify precisely which resources the new task should share with the parent task.
So you can choose what to share and what to duplicate.
Exactly. If you call clone with flags like clone a VM, share memory space, clonefs, share file system info, clone files, share open files, and clone zhand, share signal handlers, the new task behaves essentially like a thread within the same process group. If you don't share these, it behaves more like a traditional process created by fork. It's a very flexible model.
So a Linux thread is really just a task created with specific sharing flags via clone. Very neat. What about Windows?
Windows uses more explicitly layered structure for its threads. At the highest level within the kernel's executive subsystem, there's an E-thread, executive thread block. This contains accounting information, pointers to the owning process, etc.
Okay, the executive view.
Below that, in the core kernel layer, is the K-thread kernel thread block. This is where the rubber meets the road for scheduling. It holds the thread's scheduling state, priority, stack pointers for kernel mode, pointers to the E-thread, etc. This is what the scheduler primarily manipulates.
So E-thread is more management, K-thread is scheduling mechanics.
You can think of it that way. And then crucially, there's also a TEB thread environment block, which exists in user space. It contains thread-specific information needed by user mode code and libraries like thread local storage, TLS, error codes like errno or getlaster, and some performance information.
So E-thread and K-thread in kernel space, TEB in user space. A clear separation.
Yes, it highlights how thread state and management information are distributed across the user kernel boundary in the Windows one-to-one model.
And diving into Pintos, our teaching OS example, the source mentions thread switch AS being important for context switching. What's the significance of that file?
Switch S.
Yeah.
That's usually an assembly language file, and it's absolutely critical. It contains the highly optimized, low-level machine code that performs the actual context switch between threads.
The real handover.
The real handover. When the Pinto scheduler decides to stop running thread A and start running thread B, it calls a function, likely defined in switch S, that meticulously. 1. Saves all the CPU registers, general purpose segment registers, etc., of thread A onto its kernel stack. 2. Saves thread A's current kernel stack pointer. 3. Restores the saved kernel stack pointer for thread B. 4. Pops all of thread B's saved registers off its kernel stack and back into the CPU. 5. Returns, effectively resuming execution within thread B exactly where it left off. Wow. That has to be lightning fast and perfectly correct. Absolutely. It's the core mechanism enabling the illusion of concurrency on a single CPU core. It's performance critical and has to be atomic. The source also mentions how thread create in Pintos uses clever tricks, like setting up fake initial stack frames, so that when a newly created thread is switched to for the first time, it starts executing the correct function.
And there was a limitation mentioned about Pintos and floating point operations in user programs.
Yes, that's an interesting practical detail. The note says Pintos, at least in the version described, doesn't save and restore the state of the floating point unit, FPU, or newer vector registers, like SAAVX, during a thread context switch.
Why is that a problem?
Because if thread A is doing floating point calculations, gets switched out, and thread B then does its own floating point calculations, thread B might overwrite the FPU registers that thread A was using. When thread A gets switched back in, its calculations will be corrupted.
Ah, so user programs using floating point wouldn't work correctly.
Right. Real-world OCs do save and restore the FPU vector state, but it adds overhead to context switching, so simpler teaching OCs sometimes omit it. It highlights that supporting all features of modern CPUs requires careful handling in the OS kernel.
Fascinating. Okay, so we have processes, the isolated actors and threads, the lighter workers within them. They can talk via IPC. But what happens when multiple threads within the same process or processes using shared memory try to access and modify the same piece of shared data concurrently? You hinted at this earlier, sounds like a recipe for chaos.
You've perfectly captured the essence of the problem. This is the infamous critical section problem, and it's one of the most fundamental, pervasive, and often maddening challenges in concurrent programming.
Why maddening?
Because when multiple threads or processes race to access and modify shared data, the final result depends on the precise, often unpredictable, timing and interleaving of their instructions. This leads to what we call race conditions.
Races, like they're racing to update the data, and the outcome depends on who gets there first or in what order.
Exactly. And because the timing can vary, depending on system loads, scheduling decisions, and other factors, race conditions often lead to bugs that are incredibly hard to reproduce and debug. They might only appear one time in 1,000 runs, under very specific circumstances. It can make tracking them down a nightmare. Data gets corrupted and variants are broken and results become completely unreliable.
Okay, so chaos. We need to impose order. What are the absolute must-haves, the non-negotiable goals for any robust solution to this critical section problem?
There are three essential requirements that any correct solution must satisfy. 1. Mutual exclusion. This is the big one. Only one process or thread can be executing inside its critical section, the specific part of the code that accesses the shared data at any given time. If one is in, others wanting to enter must wait.
Only one chef allowed in the shared pantry at a time. Got it.
2. Progress. If no process is currently executing in its critical section, and there are some processes that wish to enter their critical sections, then the selection of the next process to enter cannot be postponed indefinitely. Furthermore, only those processes that are not executing in their non-critical code, their remainder sections, can participate in this decision. Basically, if someone wants in and the coast is clear, a decision must be made reasonably soon about who gets in next.
No deadlock or arbitrary blocking if entry is possible. Makes sense.
3. Bounded waiting. There must be a limit on the number of times that other processes are allowed to enter their critical sections after a particular process has made a request to enter its critical section and before that request is granted.
So, fairness. You can't let others keep cutting in line forever while one process starves, waiting for its turn.
Precisely. It guarantees that a waiting process will eventually get access. Mutual exclusion ensures correctness, while progress and bounded waiting ensure liveness and fairness.
Those are strict requirements. How do we even begin to achieve that kind of coordination, especially given how fast CPUs execute instructions? Seems like you could easily get interference between checking a condition and acting on it.
That's the core difficulty. Software-only solutions exist, like Peterson's algorithm, but they can be complex and may not perform well on modern hardware with its complex memory models and out-of-order execution. So we often rely on low-level tools, frequently supported directly by the hardware, that guarantee certain primitive operations are atomic.
Atomic, meaning
Meaning they execute as a single, indivisible, uninterruptible unit. From the perspective of the rest of llegamos a la conclusión de la sección del system, an atomic operation either completes entirely or it doesn't happen at all. No other process or thread can observe it in a partially completed state or interfere with it mid-execution.
like flipping a light switch, it's either on or off, never observed halfway. What are some examples of these hardware-supported atomic operations?
Two classic examples, often provided as single machine instructions on many architectures, are test and set and compare and swap.
Okay, test stands.
The test instruction atomically reads the current value of a Boolean variable, usually in memory, sets the variable to true, and returns the original value it read. The key is that the read and the write happen as one indivisible step.
How does that help with locking?
You can use a shared Boolean variable, let's call it lock, initialized to false. To enter a critical section, a thread repeatedly calls test and set and lock. If it returns false, it means the lock was false, but the instruction atomically set it to true, so this thread successfully acquired the lock and can enter. If it returns true, it means the lock was already held true, so the thread keeps trying.
Ah, okay. And compare and swap. Sounds more complex.
It is, and more powerful. The compare and swap CAS instruction typically takes three arguments: a memory location, adder, an expected current value, expected, and a new value, new. It atomically does the following. It checks that the value currently at adder is equal to expected. If it is, it updates the value at adder to new and returns success, for example, true. If the value at adder is not equal to expected, it does nothing to the memory and returns failure, read, false.
So it only swaps if the value hasn't changed since you last read it.
Exactly. It lets you detect if another thread interfered between your read and your attempted write. This is incredibly useful for implementing locks and other synchronization primitives without needing hardware locks for everything. Our source, figure 5.6, shows how CAS can be used to implement mutual exclusion. A thread reads the lock value, say 0 for unlocked, then uses CAS to try and change it from 0 to 1. If the CAS succeeds, it got the lock. If it fails, it means someone else changed the lock from 0 between the read and the CAS attempt.
Very clever. Building complex synchronization from these fundamental hardware guarantees.
It truly is. These low-level atomic primitives form the bedrock. Building upon them, operating systems provide higher-level, more programmer-friendly synchronization tools.
And probably the most common and fundamental of these OS tools is the mutex lock, right?
Yes, mutex locks, short for mutual exclusion locks, are the workhorse. They provide a simple way to enforce mutual exclusion for critical sections.
How do they work, generally?
They typically provide two primary atomic operations: acquire, or lock, and release, or unlock. A thread must call acquire to obtain ownership of the mutex before entering its critical section. If the mutex is already held by another thread, the calling thread will typically wait until the mutex is released. Once the thread finishes its critical section, it calls release to give up ownership, potentially allowing another waiting thread to acquire it.
So, acquire, do critical work, release. Only one thread can hold the lock at a time. Simple concept. But I've heard the term spin lock associated with mutexes, and you mentioned busy waiting earlier. Are mutexes always spin locks?
Not necessarily, but they can be implemented as spin locks, especially in certain contexts. A spin lock is a type of lock where a thread trying to acquire a lock that's already held simply sits in a tight loop, repeatedly checking the lock status, spinning, until it becomes free. This is busy waiting.
Wasting CPU cycles, just checking. That sounds inefficient.
It can be very inefficient, especially on a single processor system, because the spinning thread is occupying the CPU but doing no useful work, preventing the thread holding the lock from running and eventually releasing it. However,
There's a but.
on a multi-core system, if the critical section protected by the lock is expected to be held for a very short time, spinning might actually be more efficient than putting the thread to sleep and invoking the OS scheduler. Why? Because the overhead of suspending a thread, context switching to another, and then waking the first thread up again when the lock is free can be significant. If the lock is likely to be released within microseconds, it might be faster to just spin for a brief period.
The classic performance trade-off. Spin if the wait is likely very short. Sleep if it might be longer.
Exactly. It depends heavily on the expected lock contention and hold times.
How are mutexes implemented in real operating systems? Do they spin or sleep?
Often, it's a hybrid approach or configurable. Linux, for example, provides various locking mechanisms in the kernel. Its standard mutexes, struct mutex, will generally put waiting tasks to sleep, associating them with a wait queue for the mutex and invoking the scheduler. This is efficient for potentially longer critical sections. However, Linux also provides explicit spin locks, for situations where the lock hold time is guaranteed to be short, often used in interrupt handlers or very low-level code where sleeping isn't allowed.
Okay. What about user-level libraries like Threads or Windows?
Threads provides thread mutex and functions like thread mutex init, thread mutex lock, and thread mutex unlock. The exact behavior, spinning versus sleeping, might depend on the implementation or mutex attributes set during initialization. Windows offers critical sections, critical section object with initialize critical section, enter critical section, leave critical section. These are typically optimized for low contention within a single process and might spin for a short while before resorting to kernel-level waits if contention is high. Windows also provides heavier weight mutex objects for inter-process synchronization, which usually involve kernel waits. And as mentioned, Windows also has specialized Slim Reader Writer (SRW) locks optimized for read-heavy scenarios, allowing multiple readers concurrently, but only one writer exclusively.
Okay, so mutexes are great for simple one-at-a-time exclusive access. But what if you need something more versatile? Maybe controlling access to a pool of N resources or signaling between threads in more complex ways than just locked and locked?
That's where the venerable semaphore comes in. Introduced by Dijkstra back in the 60s, they're a more general synchronization tool than mutexes.
More general how?
A semaphore S is essentially an integer variable that can only be accessed through two standard atomic operations. One, wait S, often called PS, from the Dutch proberen meaning to test. Two, signal S, often called VS, from vergen meaning to increment.
Okay, wait and signal. What do they do to the integer s?
The classic definition is
While busy wait or block, s clock.
S. Both operations must be atomic, especially the checking and decrementing in wait and the incrementing in signal.
So wait waits until s is positive, then decrements it. Signal just increments it. How does that provide synchronization?
Think of S as counting the number of available resources. If you initialize a semaphore S to, say, 5, it means there are 5 units of a resource available. Each time a thread needs a unit, it calls wait S. If S is positive, the call succeeds, S is decremented, and the thread takes a resource unit. If S is 0, the thread blocks until another thread calls signal to release a resource unit, incrementing S.
Ah, so it can manage multiple resources. A mutex is basically just a semaphore initialized to 1, right? A binary semaphore.
Exactly. A mutex is logically equivalent to a binary semaphore. It can be a 0 or 1. Semaphores that can take any non-negative integer value are called counting semaphores.
And you mentioned semaphores can overcome the busy waiting problem.
Yes, that's a key implementation detail. Well, the definition I gave used a while loop suggesting busy waiting. Practical semaphore implementations in operating systems typically avoid it. When a process executes wait S and finds S is not positive, instead of spinning, the OS puts the process into a waiting queue associated with that specific semaphore and changes the process's state to waiting.
Suspends the process.
Right. The CPU scheduler is then invoked to run another process. When some other process later executes signal S, incrementing S, the OS checks the waiting queue for semaphore S. If the queue is not empty, it picks one of the waiting processes, for example, using FIFO, moves it from the waiting queue back to the ready queue, so it can eventually run again and complete its wait S operation. This avoids wasting CPU cycles.
Much more efficient for potentially long waits. Semaphores are famous for solving those classic synchronization problems, aren't they? Like the bounded buffer, readers, writers, dining philosophers.
Indeed. Their ability to act as both mutexes, when initialized to 1, and counters, makes them incredibly versatile for coordinating complex interactions between multiple processes or threads. They are powerful tools.
But powerful tools can sometimes have subtle dangers. What's this issue of priority inversion that can happen with locks or semaphores?
Priority inversion. It's a tricky scenario that can occur in priority-based preemptive scheduling systems when you use locks. Imagine you have 3 threads: high priority H, medium priority M, and low priority L.
Okay, HML.
Suppose L acquires a lock needed by H. Now H becomes ready to run. Since H has higher priority than L, H preempts L. But H cannot proceed because it needs the lock currently held by L.
So H blocks waiting for L.
Right. Now suppose the medium priority thread M becomes ready. Since M has higher priority than L, which is currently holding the lock H needs but isn't running, M preempts L and runs.
Wait, so the medium priority thread M is running, while the high priority thread H is stuck waiting for the low priority thread L, which isn't even running, to release the lock.
Exactly. That's priority inversion. The medium priority thread is effectively indirectly blocking the high priority thread. This can be disastrous in real-time systems where H might miss its deadline. The most famous example was on the Mars Pathfinder mission.
Wow, how do you solve it?
The most common solution is the priority inheritance protocol. When a high priority thread H has to block waiting for a resource held by a lower priority thread L, the system temporarily boosts L's priority to be equal to H's priority.
So L now runs with high priority.
Yes, just for the duration it holds the lock needed by H. This prevents M from preempting L, allowing L to finish its critical section quickly and release the lock. As soon as L releases the lock, its priority reverts to its original low level, and H, which was waiting, can then acquire the lock and run.
Clever. Temporarily lend priority to get the lock released faster.
It's an effective solution used in many real-time operating systems.
Okay, so we've gone from low-level hardware atomics to mid-level OS primitives like mutexes and semaphores. Are there even higher-level tools or language constructs designed to make synchronization easier and less error-prone for programmers?
Absolutely. As concurrent programming became more common, researchers and language designers sought ways to abstract away the complexities of manual locking. One influential construct is the monitor.
Monitors, what are they?
A monitor is a programming language construct. not usually a direct OS primitive, but built using them, that encapsulates shared data together with the procedures that operate on that data. Crucially, it ensures that only one thread can be actively executing any procedure within the monitor at any given time.
So the mutual exclusion is implicit, built into the monitor structure itself.
Exactly, the compiler enforces it. When a thread calls a monitor procedure, it implicitly tries to acquire the monitor's single hidden lock. If another thread is already inside the monitor, executing one of its procedures, the calling thread blocks. When a thread exits a monitor procedure, it implicitly releases the lock.
That sounds much safer. The compiler handles the locking.
It significantly reduces the risk of programmers forgetting to acquire or release locks correctly. Monitors also typically include condition variables, which allow threads inside the monitor to wait for specific conditions to become true, again, about waiting for a buffer to become non-empty, without continuously polling, and to signal other threads when conditions change. They provide a structured way to manage complex coordination within the monitor's protected environment. Java's synchronized methods and blocks are a prime example of monitor-like constructs.
Monitors sound like a big step up in structured concurrency. What about even more recent ideas?
A very active area, especially driven by multi-core challenges, is transactional memory, TM.
Transactions, like in databases.
Kind of similar concept, yes. TM allows a programmer to designate a sequence of memory read-write operations as an atomic transaction. The system, either hardware, software, or a hybrid, ensures that this sequence executes as if it were a single atomic step. If two threads try to execute transactions that conflict, for example, one reads a location that the other writes, the system detects the conflict. Typically, it will abort one of the transactions, discard its changes, and automatically retry it later. If a transaction completes without conflict, its changes are committed atomically.
So instead of locks, you just declared this block of code should be atomic, and the system figures it out.
That's the allure. It promises to simplify concurrent programming by replacing complex locking protocols with simpler atomic blocks. However, designing efficient and robust TM systems, especially in hardware, is very challenging, and it's still an area of active research and development, though some languages and platforms offer software transactional memory, STM.
Interesting. We also saw OpenMP used for implicit threading earlier. Does it have synchronization features too?
Yes, besides parallelizing loops, OpenMP provides explicit synchronization constructs. One simple one is the critical directive. If you put #pragma_omp critical before a block of code,
Although one thread can execute that block at a time.
exactly, it acts like a global mutex lock specifically for that named or unnamed critical section. For example, if multiple threads are updating a shared counter variable inside a parallel region, you could protect the update like this. See #pragma_omp critical. Counter plus is local value. This ensures the updates happen atomically without race conditions. OpenMP offers other directives too, like atomic for simple atomic updates, a barrier to make all threads wait for each other.
So OpenMP provides tools at various levels. Finally, is there a way to sort of sidestep the whole shared mutable state problem altogether?
There is, and it's gaining traction, using functional programming languages or functional styles.
How does functional programming help with concurrency?
Many functional programming paradigms strongly discourage or outright disallow mutable shared state. Data structures are often immutable once created, they cannot be changed. Operations create new versions instead of modifying old ones. Functions aim to be pure, meaning they have no side effects, like modifying global variables.
If nothing shared can be changed, then there's no risk of race conditions when multiple threads read the same data.
Precisely. If the data is immutable, threads can share it freely without any need for locks. This eliminates a huge category of concurrency bugs by design. Languages like Haskell, Clojure, Fshare, and functional styles in languages like Scala or even modern JavaScript leverage immutability and pure functions to make concurrent programming inherently safer and often easier to reason about. It's a fundamentally different approach avoiding the problem rather than solving it with locks.
Fascinating. So from hardware atomics to functional programming, a whole spectrum of tools to manage the perils of concurrency.
It's a deep and crucial area of computer science.
Okay, we've got all these processes and threads, potentially communicating, synchronizing carefully. But at the end of the day, there's usually only a limited number of physical CPU cores doing the actual computation. Often just one in simpler systems, or maybe 4, 8, 16 in modern ones, but usually far fewer cores than tasks wanting to run. So how does the operating system decide who gets to use the CPU core and when and for how long? This sounds like the job of the CPU scheduler, the system's conductor.
Absolutely. The CPU scheduler is one of the most critical components of the operating system kernel, responsible for allocating the precious CPU resource among all the competing tasks, processes, or kernel threads that are ready to run. Its decisions profoundly impact the system's overall performance, responsiveness, and fairness.
How does it know which processes are even capable of running? We talked about states earlier.
Exactly. The scheduler primarily deals with processes that are in the ready state. They're loaded in memory, not waiting for I/O, just waiting for a CPU core to become available. The scheduler maintains a ready queue, or multiple queues, as we'll see, listing these ready tasks.
And what triggers the scheduler to even make a decision? Does it run constantly?
Not constantly, but frequently. Scheduling decisions need to happen at specific points in time. We touched on this earlier, but the 4 key scenarios are: 1. When a process switches from running to waiting, for example, starts an I/O request, the CPU is now free. 2. When a process switches from running to ready, e.g., its time slice expires in a time-sharing system, or a higher priority task becomes ready. 3. When a process switches from waiting to ready, for example, its I/O request completes, this might trigger a decision if the newly ready process has higher priority than the currently running one. 4. When a process terminates, the CPU is now free.
So sometimes a decision must be made, cases 1 and 4, and sometimes it's optional or depends on the scheduling policy, cases 2 and 3.
Correct. This leads to the critical distinction between non-preemptive and preemptive scheduling.
Remind me again.
In non-preemptive or cooperative scheduling, once a process is given the CPU and is a running state, it keeps the CPU until it voluntarily releases it, either by terminating or by switching to the waiting state. The OS cannot force it off the CPU. This was common in early systems like original Windows 3.x or Mac OS.
Sounds simple, but potentially problematic if one process hogs the CPU.
Very problematic. A buggy or malicious process could monopolize the CPU, making the system unresponsive. That's why virtually all modern general-purpose operating systems use preemptive scheduling.
Preemptive meaning the OS can take the CPU away.
Yes. The OS can interrupt a running process even if it doesn't want to give up the CPU and force a context switch. This usually happens when a hardware timer interrupt occurs, signaling the end of a time slice, or when a higher priority process becomes ready. Preemption is essential for time sharing, responsiveness, and preventing system hangs.
Okay, so modern systems are preemptive. Now, when the scheduler does run, how does it choose which ready process gets the CPU next? There must be different strategies or algorithms.
Oh yes, many algorithms have been developed over the decades, each with its own characteristics, advantages, and disadvantages. They're typically evaluated based on criteria like CPU utilization, keeping the CPU busy, throughput, number of processes completed per time unit, turnaround time, total time from submission to completion, waiting time, time spent waiting in the ready queue, and response time, time from request submission until the first response is produced, crucial for interactive systems.
What are some of the classic algorithms I should know about?
Let's start with the simplest. First come, first served, FCFS.
Like a queue at the bank. First in, first out. FIFO.
Exactly. Processes are added to the end of the ready queue as they become ready, and the scheduler always picks the process at the head of the queue. It's simple to implement and understand.
Yeah.
It can suffer from the convoy effect. If a very long-running process, a truck, gets the CPU, many shorter processes, cars, might arrive and get stuck waiting behind it for a long time, even though they could finish quickly. This leads to poor average waiting time and poor responsiveness for the short processes. FCFS is also non-preemptive by nature.
Okay, simple but potentially unfair to short jobs. What tries to fix that?
Shortest job first, SJF. The idea is to pick the process that has the smallest next CPU burst predicted.
Give priority to the quickest tasks first.
Right. This algorithm is provably optimal in terms of minimizing the average waiting time for a given set of processes. If you want the best average throughput, SJF is theoretically the way to go.
Sounds great. What's the catch?
The catch is predicting the future. How do you know the exact length of the next CPU burst for each process? You can't, really.
So it's usually estimated.
Yes. Typically based on the process's past behavior, often using a technique called exponential averaging to give more weight to recent bursts. But the estimate might be inaccurate. Also, SJF can suffer from starvation for long jobs if there's a continuous stream of short jobs arriving.
Can SJF be preemptive?
Yes. The preemptive version is often called shortest remaining time first, SRTF. If a new process arrives in the ready queue with a predicted next CPU burst length that is shorter than the remaining time needed by the currently running process, the scheduler preempts the current process and runs the new, shorter one. Our source shows a Gantt chart example where SRTF yields a better average waiting time, 6.5 meters, compared to non-preemptive SJF, 7.75 meters, for the same set of processes, demonstrating the benefit of preemption here.
Okay, FACS, SJFS, RTF. What about explicitly using priorities?
That's priority scheduling. Each process is assigned a priority value, an integer usually, and the scheduler always picks the ready process with the highest priority. Sometimes low numbers mean higher priority, sometimes higher numbers do, depends on the system.
Seems intuitive. Give important jobs preference. SJF is kind of like priority scheduling, where priority is based on predicted burst length.
Exactly. Priority scheduling is a general concept. It can
Alright.
be preemptive. If a higher priority process arrives, it preempts the running lower priority one, or non-preemptive.
Main problem here, you mentioned it before, starvation.
Yes, starvation is the major drawback. Low priority processes might wait indefinitely if there's a constant supply of higher priority processes arriving. A common solution is aging.
Aging. Like fine wine.
Sort of. The idea is to gradually increase the priority of processes that have been waiting in the ready queue for a long time. Eventually, even a low priority process will age enough to reach a high enough priority to get scheduled, thus preventing starvation.
Clever workaround. Now, for interactive time-sharing systems where everyone needs a fair shot relatively quickly, what's the go-to algorithm?
I would be round robin,
Yeah.
RR. It's designed specifically for time-sharing environments.
How does round robin work?
It's basically FCFS, but with preemption based on a time limit. Each process gets a small, fixed unit of CPU time called time quantum, or time slice, typically somewhere between 10 and 100 milliseconds.
Okay, a small slice of time.
When a process is scheduled, a timer is set for the length of the quantum. If the process is still running when the timer interrupt goes off, the OS preempts it, moves it to the end of the ready queue, and schedules the next process from the head of the ready queue. If the process finishes its CPU burst before the quantum expires, it releases the CPU voluntarily, and the scheduler runs the next process.
So everyone gets a turn cycling through the queue. Seems fair. What determines how well it works?
The critical parameter is the size of the time quantum. If the quantum is very large, really giant seconds, RR degenerates towards FCFS. If the quantum is very small, example close to the context switch time itself.
You spend all your time switching contexts instead of doing useful work.
Exactly. The overhead becomes excessive. So you need a quantum that's large enough relative to the context switch time to keep overhead low, but small enough to provide good responsiveness for interactive users, so they don't wait too long between turns. Finding the sweet spot is key.
FCFS, SJF, priority, round robin. Are there more complex algorithms that try to combine ideas?
Yes, especially in real-world systems. Multi-level queue scheduling partitions the ready queue into several separate queues. For example, you might have a high-priority system processes queue, a medium-priority interactive processes queue, and a low-priority batch processes queue.
And each queue might have its own scheduling algorithm.
Correct. The interactive queue might use round-robin for responsiveness, while the batch queue might use FCFS. Scheduling also needs to happen between the queues, usually with fixed priority. Example, always serve the system queue first, then interactive, then batch. The risk here is starvation for lower priority queues.
How do you fix that?
One way is to give time slices to queues. Example, interactive queue gets 80% of CPU time, batch gets 20%. Another more flexible approach is the multi-level feedback queue.
Feedback. Does that mean processes can move between queues?
Precisely. This is a very common and sophisticated approach. Processes can move between different priority queues based on their behavior. For example, a process might start in a high priority queue with a short time quantum. If it uses its full quantum, indicating it's CPU bound, it might get moved down to a lower priority queue with a longer quantum. If a process in a lower queue gives up the CPU quickly for I/O, indicating it's interactive, it might get moved up to a higher priority queue.
So it adapts. It tries to separate interactive I/O-bound jobs from CPU-bound jobs and treat them appropriately, while also using aging to prevent starvation in the lowest queues.
Exactly. It's complex to tune, but it's very effective at balancing responsiveness, throughput, and fairness, which is why variations of it are used in many operating systems.
Okay, that covers scheduling processes or kernel threads. What about scheduling user-level threads when the kernel isn't directly aware of them, like in the many-to-one or many-to-many models? Who schedules those?
That distinction brings us to the concept of scheduling scope.
Hmm.
When you have user-level threads managed by a thread library, the scheduling of these user threads onto the available kernel-level entities, like LWPs, is handled by the thread library itself, running in user space. This is called Process Contention Scope, PCS.
Process contention, meaning the contention for CPU time, happens among threads within the same process.
Yes, the user-level thread library acts like a mini scheduler, deciding which of its threads gets to run on the underlying kernel entity, without the kernel's involvement or knowledge of the individual user threads.
And if the kernel does manage the threads directly, like in the one-to-one model?
Then the kernel itself schedules these kernel-level threads onto the physical CPUs. This is called System Contention Scope, SCS. Here, the competition for CPU time happens among all threads in the entire system, regardless of which process they belong to. The kernel considers all ready kernel threads across all processes when making its scheduling decisions.
And you said earlier that modern systems like Windows, Linux, and Solaris use the one-to-one model, so they use SCS.
That's correct. Because they map each user thread to a kernel thread, the kernel's main scheduler is directly responsible for managing contention among all threads system-wide using SCS.
Makes sense. Now, shifting gears slightly, what about real-time CPU scheduling? This isn't just about being fast on average, it's about meeting deadlines, right? Sometimes critical ones.
Absolutely. Real-time systems, found in things like industrial control, avionics, medical devices, robotics, and multimedia systems, have fundamentally different requirements. They often deal with hard, real-time tasks, where missing a deadline is a system failure, potentially catastrophic, or soft real-time tasks, where missing a deadline is undesirable but not fatal. Jury example, dropping a video frame.
So the scheduler needs to be predictable.
Predictability is paramount. The primary goals are to guarantee that critical tasks complete by their deadlines and to minimize latency. Two key latency metrics are interrupt latency, the time from an interrupt arriving to the start of the routine that services it, and dispatch latency, the time it takes for the scheduler to stop one process and start another. Real-time OCs need to keep these latencies bounded and minimal.
How do they achieve this? What kinds of algorithms are used?
Real-time scheduling usually relies on preemptive priority-based algorithms, but the priorities are often assigned based on the task's timing requirements. Two classic algorithms are rate monotonic, RM scheduling, and earliest deadline first, EDF scheduling.
Rate monotonic, priority based on rate.
Yes, RM is a static priority algorithm used for periodic tasks that need to run at regular intervals. It assigns higher priority to tasks with shorter periods, higher rates. It's relatively simple to implement and analyze.
And earliest deadline first.
EDF is a dynamic priority algorithm. At any point in time, it assigns the highest priority to the ready task that has the closest upcoming deadline.
Which one is better? The sources had those figures comparing them, figure 6.18 and figure 6.19.
EDF is theoretically optimal in the sense that if a set of tasks could be scheduled to meet all their deadlines by any algorithm, EDF can do it. RM is not optimal. There are task sets that RM cannot schedule successfully, even though a valid schedule exists. The figures illustrate this. They show a scenario where EDF successfully schedules two tasks to meet their deadlines, while RM fails because its static priority assignment leads to the longer period task missing its deadline. EDF, by dynamically prioritizing based on urgency, closeness of deadline, handles the situation correctly. However, EDF can be more complex to implement.
Okay. RM is simple but suboptimal. EDF is optimal but more complex. What about modern general-purpose OS schedulers, like in Linux? They need to balance interactive performance, batch throughput, fairness. It sounds incredibly complex.
It is. Linux, for instance, has evolved its scheduler significantly. Since kernel 2.6.23, the default scheduler for normal tasks is the completely fair scheduler, CFS.
Completely fair. How does it achieve fairness?
It takes a really interesting approach. CFS doesn't use fixed time slices or traditional static priorities in the same way. Instead, it tries to give each task a fair proportion of the processor time. It does this by tracking the virtual runtime for each task.
Virtual runtime.
Think of it as the amount of time a task would have run if it were on an ideal, perfectly fair processor. CFS always tries to run the task that has the lowest runtime, the one that has run the least so far relative to its fair share.
So it always picks the task that's furthest behind on getting its fair share?
Exactly. Tasks with lower niceness values, higher priority in traditional terms, accumulate runtime more slowly, meaning they get chosen more often. Tasks with higher niceness, lower priority, accumulate runtime faster, so they run less often. But importantly, every task eventually gets to run because its runtime will eventually become the lowest. It elegantly avoids starvation while providing proportional fairness based on niceness values. It also uses preemptive scheduling. If a task wakes up with a lower runtime than the currently running task, it can preempt it.
That sounds remarkably clever, tracking virtual time to ensure fairness. What about Windows? How does its scheduler handle the mix?
Windows uses a priority-based preemptive scheduler with 32 priority levels. It groups these into priority classes, like real-time in priority class, high priority class, normal priority class, idle priority class. Threads inherit a base priority from their processes class, but can have relative priorities within that class.
And does it adjust priorities dynamically?
Yes, Windows employs dynamic priority boosting quite significantly, especially to enhance responsiveness. For example, when a thread waiting for certain types of I/O, like keyboard or mouse input or completing a network read gets woken up, the scheduler temporarily boosts its priority
Why?
to ensure that the thread handling your interactive input gets to run very quickly, making the system feel responsive. Threads associated with the foreground window, the one you're actively using, also typically receive priority boosts over background threads. These boosts are temporary. The priority decays back down over time if the thread doesn't continue to be interactive.
So it actively tries to prioritize the user experience. That makes sense. And Windows 7 introduced user mode scheduling.
Yes, user mode scheduling, UMS, was added to allow certain applications, particularly those using runtime libraries designed for highly scalable task-based parallelism, like Microsoft's ConCRT for C++, to essentially bypass the kernel's main scheduler for managing their own internal pool of threads. It gives sophisticated runtimes more control over scheduling decisions within their process, potentially reducing kernel transitions and overhead for specific workloads.
Okay, a very complex and fascinating world, CPU scheduling. It's amazing how much goes into just deciding who runs next.
It's a constant balancing act between competing goals.
So we've covered the actors, processes, threads, how many talk, IPC, how they stay synchronized, and how the OS manages their time on the CPU. But there's one more enormous piece of the puzzle: memory. Every process needs memory to store its code, data, stack, heap, sometimes lots of it. Often, the total memory demanded by all running processes far exceeds the actual physical RAM available on the machine. How does the system handle this? How does it give every process the illusion that it has a vast private memory space all to itself, even when physical memory is limited and shared?
That, my friend, is the magic and the power of virtual memory. It's arguably one of the most fundamental and ingenious abstractions provided by modern operating systems.
Virtual memory, creating an illusion of more memory than exists.
Exactly. It's a memory management technique that allows each process to operate within its own private, contiguous virtual address space, which can be, and often is, much larger than the physical memory, RAM, actually installed in the computer.
So my program thinks it has, say, gigabytes of continuous memory, even if my machine only has a few gigabytes of RAM, and that RAM is fragmented and shared by many processes.
Precisely. Virtual memory effectively decouples the logical addresses used by the program, virtual addresses, from the physical addresses where data is actually stored in RAM, physical addresses. The OS, with crucial help from hardware, the Memory Management Unit, or MMU, handles the translation between virtual and physical addresses on the fly.
It's like giving every resident their own unique building address scheme virtual, while the Postal Service, OSMMU, knows how to map those addresses to actual physical apartment locations, physical RAM, even if those apartments are scattered across different buildings or some mail needs to be fetched from a remote warehouse disk.
That's a fantastic analogy. It captures the mapping and the potential need to fetch things from slower storage. This abstraction provides several key benefits. 1. Isolation. Each process's virtual address space is private. One process cannot directly access another's memory, enhancing protection. 2. Illusion of large memory. Processes aren't limited by physical RAM size. 3. Simplified programming. Programmers don't need to worry about where their code data physically resides. 4. Efficient sharing. Allows sharing of libraries or memory regions between processes, like shared memory or copy on write.
How does it handle the more memory than physically exists part? Where does the extra data live?
That's achieved primarily through a technique called demand paging.
Demand paging, meaning pages are loaded only when demanded.
Exactly. The virtual address space of a process is divided into fixed size blocks called pages, VG4KB. Physical memory is divided into blocks of the same size called page frames. The OS only loads a virtual page from disk, where the full program image or swapped-out data resides, into a physical page frame in RAM the first time the process actually tries to access an address within that page.
So it doesn't load the whole program at startup?
Not usually.
Oh.
Only the parts needed immediately. When the process tries to access a virtual address whose corresponding page is not currently in a physical frame, the page table entry indicates it's invalid or on disk.
The hardware triggers a page fault.
Correct. The MMU detects the invalid access and generates a trap, a page fault, to the operating system.
Is a page fault an error?
Not necessarily. It's often just the OS's signal that it needs to perform demand paging. The OS's page fault handler routine then takes over. It figures out which virtual page was accessed, finds where that page's content is stored on disk, either in the original executable file or in a special disk area called the swap space or paging file.
Okay, finds it on disk.
Allocates a free physical page frame in RAM. If there are no free frames,
Uh-oh. Then what? Kick something else out.
then the OS must perform page replacement. It uses a page replacement algorithm, like LRU, least recently used, FIFO first in, first out, clock, or others, to select a victim page currently in memory, preferably one not recently used, to evict. If the victim page has been modified since it was loaded, its contents must first be written back to the swap space on disk.
Okay, finds a frame, possibly by evicting a victim, loads the needed page from disk into that frame, updates the process's page table to map the virtual page to the now resident physical frame, and then
the OS restarts the instruction that originally caused the page fault.
Oh, yeah.
This time, the virtual address access will succeed because the page is now in memory and the process continues execution, completely unaware that a page fault in disk I/O just occurred, except for the delay.
That's incredible. Transparently handling memory fetches from disk. Our Pinto source mentions its page fault. Handler needs to be quite sophisticated, handling fetches from both the executable file and swap space. It also stressed that page fault handling should allow for parallelism.
Yes, that's critical for performance. Handling a page fault involves slow disk I/O. While one process is blocked waiting for its page to be read from disk, the OS absolutely must be able to schedule other ready processes to run on the CPU. Otherwise, the entire system would grind to a halt during page faults. A robust page fault handler is a cornerstone of any virtual memory system.
The source also mentioned Pintos's load segment function using page read bytes and page 0 bytes when setting up virtual pages for an executable. How does that relate?
That relates to how the initial virtual pages for the code and initialized data segments are set up for demand paging. When load segment maps a page, it doesn't load the data immediately. It just sets up the page table entry to know where on the executable file the data lives. Page read bytes tells it how much data is in the file for that page and how much of the rest of the page should just be initialized to 0, page 0 bytes. The actual read from the file only happens later via the page fault handler when the page is first accessed. Lazy loading setup, very efficient. Now, virtual memory helps with the illusion of large memory. Does it also help optimize process creation? We talked about fork, potentially copying a huge address space.
Yes. Virtual memory enables a crucial optimization for fork called copy on write, COW.
Copy on write. We mentioned it briefly with sharing. How does it apply to fork?
Instead of physically copying all the parent process's pages into new page frames for the child when fork is called, which is incredibly wasteful if the child immediately calls exec, CRW takes a clever shortcut.
What's the shortcut? Initially, fork creates the child's page table, but instead of allocating new frames and copying data, it makes the child's page table entries point to the same physical page frames that the parent is using.
So parent and child initially share all their pages.
Exactly. But, crucially, the OS marks these shared pages in both page tables as read-only.
Read-only, even if they were writable before.
Yes. Now, if either the parent or the child attempts to write to one of these shared read-only pages,
It triggers a page fault.
yeah, precisely, a special kind of page fault. The page fault handler recognizes this is a copy on write fault. It then allocates a new physical page frame, copies the contents of the original shared page into this new frame, updates the page table of the process that tried to write to point to this new frame, and marks it as writable again, and then resumes the write operation.
So a physical copy is only made if and when one of them actually tries to modify the page. Brilliant.
It's incredibly efficient. If the child calls exec right away, no pages, or very few, might ever need to be copied. If they mostly just read shared data, they continue sharing. Copying only happens for pages that are actually written to, deferring the cost until it's absolutely necessary. Our textbook illustrates this nicely in figures 9.7 and 9.8, showing the shared pages initially and the duplication after a write.
That's a huge performance win for fork. It must require specific hardware support in the MMU, though, to mark pages read-only and detect the write attempts.
Absolutely. The MMU needs to support read-write protection bits in the page table entries and generate the necessary fault on a write to a read-only page. Modern processors all provide this capability, making CIW a standard technique.
Okay, CIW is great. What are some of the other major challenges or performance pitfalls related to virtual memory and paging? Something called thrashing.
Thrashing. That's the nightmare scenario for a virtual memory system.
What is it?
Thrashing occurs when a system spends almost all its time moving pages between RAM and disk, paging, and very little time actually doing useful computation. It happens when the combined memory demands of the active processes, their working sets, the pages they need currently, significantly exceed the available physical RAM.
So processes are constantly page faulting.
Yes, a process runs for a tiny fraction of a second, hits a page fault, waits for disk I/O. While it waits, another process runs, hits its page fault, waits. The disk queue becomes enormous, the CPU sits idle most of the time waiting for pages, and system throughput plummets. The system feels incredibly sluggish or frozen.
It's a vicious cycle of page faults leading to low CPU utilization, which might even trick a naive OS into admitting more processes, increasing multiprogramming, making the memory pressure even worse.
Exactly, that's the downward spiral of thrashing. The solution usually involves reducing the degree of multiprogramming, suspending some processes, or adding more physical memory. Understanding working sets and preventing thrashing is critical for OS memory management.
What about page size? Does choosing 4KB versus 16KB versus 1 MB pages make a difference?
It involves significant trade-offs. Smaller pages, for example 4KB, Pro.
Yeah.
Better fit for locality of reference, less unused data loaded per page, less internal fragmentation, less wasted space within the last page allocated to a data structure. Con, larger page tables needed, more entries to cover the same virtual space, potentially more page faults, though each transfers less data, higher overhead for TLB misses, larger pages, ex 4KB, 1 MB, even 1 GB huge pages. Pro, smaller page tables, reduced TLB misses, each TLB entry covers more memory, potentially higher I/O efficiency, transferring larger blocks. Con, worse locality, more potentially unused data loaded, more internal fragmentation.
So there's no single perfect size.
No, it depends on the workload, memory size, and hardware. There's been a trend towards supporting multiple page sizes, allowing the OS or application to use larger pages for things like large data buffers or code segments where it makes sense.
And the TLB reach? You mentioned the translation look-aside buffer, TLB, is a hardware cache for page table entries. What's its reach?
The TLB is crucial for performance because accessing the full page table, which might be in RAM, for every memory reference would be far too slow. The TLB caches recent virtual to physical address translations. The TLB reach is the total amount of memory that can be accessed using only entries currently in the TLB. It's calculated as number of TLB entries, page size.
Why does reach matter?
If a process's working set, the pages it's actively using, is larger than the TLB reach, it will experience frequent TLB misses. Each TLB miss requires accessing the slower main page table, significantly degrading performance, especially for memory-intensive applications. Larger page sizes, or larger TLBs, increase the TLB reach, which is important for handling large data sets or complex programs efficiently.
Okay, final Pintos question. The virtual memory project involves modifying system calls to handle user memory pointers safely, even if the pointed to page isn't resident. This sounds tricky. The kernel itself could hit a page fault while trying to read user data.
It's indeed a significant challenge. When the kernel needs to read from or write to a buffer specified by a user pointer, for example in a read or write system call, it must first validate that pointer.
Yeah.
But even if valid, the page might not be in memory. The kernel code accessing that user pointer must be prepared to handle a page fault occurring within the kernel itself. The page fault handler needs to recognize this situation, fetch the user page, and resume the kernel operation. It requires very careful coding to avoid deadlocks or inconsistencies.
And the project also mentions implementing map, the memory mapping function. What are some common failure conditions for map?
MAP is powerful, but has strict requirements. Common failures include trying to map at address 0, often disallowed, providing a starting address or length that isn't page-aligned, requesting a mapping that would overlap with an existing mapping in the process's address space, trying to map standard input-output file descriptors, 0 or 1, trying to map a file opened only for writing with read permissions, or vice versa, if permissions conflict, insufficient virtual address space, or physical resources. Handling these errors correctly is vital for a robust map implementation.
Wow. Virtual memory is truly an intricate dance between hardware and software to create a powerful illusion.
It really is. It's the foundation that makes modern multitasking operating systems feasible, efficient, and secure.
What a journey we've been on today. We've really taken a deep dive, pulling back the curtain on the operating system's internal machinery. Feels like we covered a lot of ground for anyone heading into an OS class.
Indeed. We started with processes exploring them as these isolated, robust units of work, each with its own memory space, resources, and life cycle. The fundamental actors.
Right, the chefs in their own stations. Then we brought in threads as their lighter, more collaborative counterparts. Multiple chefs at the same station sharing resources but working in parallel, enabling concurrency within a process.
And once we had these actors, we saw how they need to communicate. We explored the whole world of inter-process communication, IPC, the trade-offs between the raw speed and danger of shared memory versus the structured exchanges of message passing, and how things like sockets and RPCs extend communication across networks.
Then the critical issue of synchronization. How do we prevent chaos when threads or processes access shared data? We looked at everything from low-level hardware atomics, test and set, compare and swap, to OS primitives like mutexes and semaphores, tackling issues like busy waiting and priority inversion, and even higher-level constructs like monitors and transactional memory that try to make concurrency safer for programmers.
And we can't forget the conductor, the CPU scheduler. We unpacked how algorithms like FCFS, SJF, priority, round robin, and sophisticated multi-level feedback queues decide who gets the CPU and when, balancing fairness, throughput, and responsiveness. We even touched on real-time scheduling needs and modern approaches like Linux's CFS.
Finally, we peered into the magical world of virtual memory, revealing how the OS and hardware conspire to give each process the illusion of a vast private address space, using demand paging, page replacement, and clever optimizations like copy on write, while navigating pitfalls like thrashing.
It's a lot, but these concepts aren't just theoretical exercises for your class. They are truly the bedrock of every application you use, every device you interact with, every single day.
Yeah, understanding them really helps demystify how incredibly complex software manages to run so smoothly and reliably most of the time. It gives you a much deeper appreciation for what's happening under the hood.
And hopefully makes you a more informed user and potentially a better programmer or system designer because you understand the constraints and mechanisms at play.
Definitely. It's incredible to think about the layers of abstraction and sheer ingenuity involved. So, as we wrap up today's deep dive, here's a provocative thought for you, our listener, to ponder.
Uh-oh.
As we continue to push the boundaries of computing, think massive AI clusters, globally distributed systems, the Internet of Things, maybe even quantum computing down the line, how might these fundamental concepts of process and thread, born in an earlier era, need to evolve?
Interesting question.
Will the strict isolation of a process still make sense? Will the shared memory model of threads be sufficient? Or will we need entirely new paradigms for defining, managing, and synchronizing concurrent units of work in environments where computation is vastly more distributed, heterogeneous, and perhaps even non-deterministic, blurring the lines between local and remote, hardware and software, maybe even human and machine intelligence?
That's a deep one. The core needs managing execution, allocating resources, ensuring correctness will persist, but the abstractions we use, the very definitions of process and thread, might undergo some profound transformations to cope with that future complexity.
Food for thought indeed. Thank you for joining us on the deep dive. We hope this exploration has equipped you with the knowledge and confidence you need for your class, and perhaps given you a new perspective on the silent, complex ballet happening inside your devices every second.
Until next time, keep digging deeper.